Hello everyone, in this video lecture we'll be learning about the different sources of noise and the quantum limit of detection. To start with, we have three different sources of noise that are associated with photodiode receivers. One is quantum noise or short noise, the other one is the noise that is associated with the dark current, the other one is the thermal noise. So first we'll learn what is about the short noise or the quantum noise. The short noise or the quantum noise arises from the photoelectrons that are being generated when the light falls on the photodetective material. As you all know, there is a the randomness associated with the photoelectrons that is generated when the light is being incident. Because of these random nature of these photoelectrons, there is a noise associated with it. That noise is called the quantum noise or the short noise. This random nature, the statistical nature of the photoelectrons is usually analyzed by the Poisson process. So, because of this noise, this is coming with the photoelectrons that are being generated when the light is incident on the photodiode. This noise or the short noise has a direct linkage with the photo detection process. That is, it sets a lower limit on the receiver sensitivity when all other conditions are optimized. The next type of noise that are associated in the photodiode receivers are the noise from the dark current. Dark current is that current that flows through the photodiode when no light is incident on the photodetective material. Okay, that current, because of that current, there is a noise associated with it. And again, mentioning in avalanche photodiodes, these carriers also get accelerated by the electric field across the device and therefore are multiplied by the avalanche mechanism. What does mean is that in avalanche photodiode we have already discussed about the multiplication that happens because of the multiplication, the dark current that is associated with APD can also get multiplied. Next is the thermal noise. The thermal noise is nothing but the noise that is associated with the temperature of the photodetector material. Thermal noise is common in all electronic devices. Now we'll see the current associated with the thermal noise. If I is the current associated with the thermal noise, and sigma square thermal is the variance for the thermal noise, and then if R is the resistor which has a temperature T, and the I square thermal is equal to sigma square thermal, that is equal to the variance that is equal to 4 into kBT into BE by R, where kB is the Boltzmann constant, B is the bandwidth, T is the temperature in Kelvin, and R is the resistance. Now the short noise, for current in the short noise, I short is equal to sigma square short, that is equal to 2Q IP BE M square F of M, where IP is the photocurrent, B is the bandwidth, M is the multiplication factor, and F of M is the avalanche photodiode noise figure. Okay, next is the dark current. The dark current ID square D or sigma square D, variance of dark current, is equal to 2Q ID M square FM into VE, where Q is the charge of the electron, M is the multiplication factor, FMD is the noise figure, and B is the bandwidth. For pin photodiode, the multiplication factor and F of M is always equal to 1. So again, to find the signal to noise ratio, we have to sum of all these noises. That is, I square N is equal to your total noise, the total the photo detector noise current I square N is equal to I square of short noise plus I square of dark current plus I square of thermal noise. So you can see a signal to noise ratio is equal to I square P M square by the total current, where IP is a photo current and M square is the multiplication factor. So you can get the signal to noise ratio for a photo detector. So the next topic for discussion is quantum limit of detection. So when you are dealing with the quantum limit of detection, first we have to understand what is an ideal detector. For an ideal detector, there will be no thermal noise, no dark current noise, or no short noise. That is, it will be having 100% quantum efficiency. There won't be any thermal noise or no dark current noise or any short noise for an ideal photo detector. And also for an ideal receiver, when one bit is being identified without an error, as long as one photon is detected. That means when one photon is detected, that means we have identified one bit without any error. So an error is made. An error comes up for the receiver only if a bit fails to produce even one electron hole pairs or photogenerators. Okay, for such small number of photons and electrons, short noise statistics cannot be approximated by Gaussian distribution. For that, we have to use Poisson statistics, because for one bit we have to produce one electron hole pair. For such small number of photons or electrons, Gaussian noise cannot be we cannot approximate this using Gaussian distribution. For that, we have to go for Poisson statistics. Okay, if NP is the average number of photons in each one bit, the probability of generating m electron hole pair is given by the Poisson distribution as P of m is equal to e raised to minus np by n the whole raised to m by m factorial. And the bit error rate can be found out by using Br is equal to half of P of 0 by 1 plus P of 1 by 0. So from the above equation, we can find out what is BR. So the different terms in BR is P of 1 of 0 and P of 0 1. So what is P of 1 of 0? 1 of 0 is that we are identifying 1 when 0 is being transmitted. When 0 is transmitted, we are identifying it as 1, but that is an error. In that case, since there is no electron or hole pair is generated, because we are transmitting 0 and we are receiving 1 as an error. So when the input bit is 0, that means there is no electron hole that is being generated. That means NP is 0. And the other condition is P of 0 1. P of 0 1 is that we are getting 0 whatever it is being transmitted. Okay, so P of 0 1 is equal to expression of minus NP, and for that the bit error rate is given by BR is equal to expression of minus NP by 2. That is, we are substituting P of 0 1 as expression minus NP. So for bit error rate less than 10 raised to minus 1, the number of the NP must exceed 20. Since this requirement is a direct result of quantum fluctuations associated with the incoming light, this is referred to as the quantum limit. So for the bit error rate to be less than 10 raised to minus n, the NP should never must exceed 20. The NP must exceed 20, and this requirement is a direct result of quantum fluctuations associated with the incoming light, and that is being referred as the quantum limit. So each one bit must contain at least 20 photons to be detected with a bit error rate of 10 raised to minus 9. This is a standard requirement, and that is called the quantum limit. This requirement can be converted into power by using P1. The expression for P1 is equal to NP h nu b, where b is the bit rate and h nu is the photon energy. And the receiver sensitivity P bar receiver is equal to NP h nu b by 2. That can be also written as NP bar h nu b, where the quantity NP expresses the receiver sensitivity in terms of average number of photons per bit, and that can be related as NP. NP bar is nothing but NP by 2, where 0 bits carry no energy.